Well, good morning. Here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. This will be the 31st lecture in the video series, and we are reaching the end of our semester, so only a few more of these to go. Alright, so let us begin. Today I have a few objectives. One, I want to look at how the Darcy-Weisbach equation can be applied to non-circular pipe or conduit, and second, I wish to look at how to calculate minor losses for pipe systems, for pipe flow systems. So we've mentioned minor losses before. We never actually sat down and learned how to calculate them or learned how to apply the formulas for them, etc., etc. So first, let's knock out the non-circular conduit. That one's fairly straightforward. So non-circular conduit. So for example, a rectangular conduit. All right, so I'm going to look at a, first of all, I'm going to look at a rectangular cross-section with height A and width B. So I have a rectangular cross-section of height A and width B. Let me label that. So it's going to have height A and width B. And if we want to remember our, so again, this is, I'll just note this is a rectangular cross-section. So this might be something like an air duct or maybe a concrete pipe for, storm drain purposes, that kind of thing. A rectangular cross-section. And then I might, I would want to be, so basically what I want to be able to do though is, I want to be able to apply the Darcy-Weisbach equation, which is again as follows. The Darcy-Weisbach equation, or Weisbach if you prefer, the German, would be head loss major equals FLV squared divided by 2GD. However, this is for circular pipes. So this equation is has been developed for circular pipes. So your standard round tubes, pipes, conduits, all of that kind of thing. However, we want to be able to learn how to apply this for non-circular pipes. And we're going to use a different value for our friction factor here. Oh, sorry about, nope, that didn't work out. Just a second here. Okay, and then if I was looking at laminar flow, if I want laminar flow, I want to be able to transform this into something slightly different. Laminar flow here. And let us consider this here. Well, the friction factor is going to be equal to this. So friction factor the friction factor F again will be F. Now the equation is going to be slightly different for this here. It's going to be C divided by the Reynolds number, hydraulic, or Reynolds number H. And so that what this high H stands for is hydraulic diameter, and C is going to be a constant from your text. C from table 8.3 in the text. I believe that's accurate. I may need to double check that. That may be for an older edition. Table 8.3 in the text. And the Reynolds number is going to be calculated slightly differently. So this is just going to be a constant that is used for different types of materials and such. The Reynolds number, assuming laminar flow, is going to be rho v dh, which is the hydraulic diameter, which is something we'll have to learn how to calculate, divided by mu. Or another way, or Reynolds number for the hydraulic diameter case, that's what the H stands for, it's the hydraulic diameter case, is V dH over nu. Over nu. Nope, that's not nu, but nu. And so then the hydraulic diameter, which is our d sub h, is sort of a way of calculating an equivalent circular cross-section for a rectangular or other shape. So the hydraulic cross-section, or sorry, hydraulic diameter, I should say, the hydraulic diameter is going to be dH is equal to 4A over P, where A is the cross-sectional area, the actual cross-sectional area, and P is the wetted perimeter. And this means the perimeter of the pipe conduit that is in contact with water. So that is the perimeter of the pipe that is in contact with water. Okay? So using that, and we'll look at this. Let me give you an example of how this hydraulic diameter works. Well, we have for if we have a rectangular pipe, and it would be different for really any type of cross section, but for a rectangular pipe, again, DH is going to be equal to 4A over P. And let's say we had a rectangular pipe that was entirely full of water, and 4A is the cross-sectional area, so that's just going to be 4A times B. That is the cross-sectional area of the pipe. But then the wetted perimeter would be A plus B plus A plus B. Or 4AB over 2A plus 2B, or just 2AB over A plus B. Although do keep in mind, this assumes the pipe is completely full. Assumes pipe is completely full. If this wasn't completely full, we would actually say calculate it off of only the wetted perimeter. So for example, if we had a pipe like this that was only filled halfway, then our wetted perimeter would only be literally the wetted perimeter, the length of that channel that is well wetted. So it would be this cross-sectional area here and the wetted perimeter here. So what we're doing essentially is more or less finding an equivalent circular area, or it's an approximately equivalent circular diameter. Then I want to find the major loss. So then the major loss equation, again, will just be combining all this together. Well, I will get that HL major is equal to FLV squared over 2 G times the hydraulic diameter. FLV squared over 2 GDH. All right, so that was the case for laminar flow. What about the case for turbulent flow? So everything up to there was laminar flow for rectangular pipes. Well, turbulent flow isn't going to be that different. Turbulent flow for non-circular pipes for non-circular pipes, and we'll say that we're going to still use the Moody chart. We'll just modify our inputs slightly. So we'll say that the Reynolds number is equal to rho v dH divided by mu, and our epsilon and our relative roughness will be epsilon over the hydraulic diameter, so epsilon over dH. And we will feed both of these into the Moody chart, and from this we will get our friction factor. And from this we'll get the friction factor F. And again, we'll still have the same equation for major head loss. And this is going to be just HL major equals FLV squared over 2G DH. 2G DH. Same idea. Okay. So let me work through a quick example here, and we'll see how all of this works together. Okay, so let us say we have a square conduit. We're going to have a square conduit that is 0.3 meters wide and 0.15 meters high. So I guess, sorry, a rectangular conduit rather than a square conduit. That would be a very poorly constructed square. If it were intended to be a square, it would almost be built like one of my drawings is drawn. So anyway, so 15 centimeters high and 30 centimeters wide. And we have, this is flowing through a conduit, a square conduit made of galvanized iron for some odd reason. Galvanized iron, galvanized iron. So the flow is going through this conduit like so. And the length of this pipe is, the length of this conduit, if I want to be consistent, is going to be 12 meters. So again, I have a square channel or a square conduit that is 12 meters long, and it is made of galvanized iron. And guess what fluid it is? Mercury. That would be interesting, but it could be water. But actually, I'm gonna say, what is one real major application we use for square conduits or rectangular conduits? We could use storm sewers, although I guess I'm getting ahead of myself. I guess you can't read my mind, but I'm just talking air. Ordinary air. So I guess I'm a bit of an airhead. So anyway, let's say Q is 0.068 cubic meters a second, cubic meters per second, and the viscosity of air will be 1.79 times 10 to the negative fifth Newton seconds per square meter, and rho air is going to be equal to 1.23 kilograms per cubic meter. Kilograms per cubic meter. Now, I'm going to make an assumption which isn't perfectly true, but I'm going to make an assumption so that I can use the tools that I have available here. And I'm going to assume that air is not compressible, which it obviously is, but maybe for our purposes it's moving slow enough that it won't be compressing, that kind of thing. So all of this is given, and I'm also told to assume that air is incompressible, and then I am asked to find the major head loss, HL major. Okay, so I'm going to work through that on the next slide. So solution. Well, the Darcy-Weisbach equation will state, again, our modified Darcy-Weisbach equation. Our modified Darcy-Weisbach will show this, that HL major is equal to FLV squared, that was a very bad L, FLV squared divided by 2 times G times the hydraulic diameter DH. DH here. And then I want to review the hydraulic diameter and calculate that. So the hydraulic diameter then DH is going to be equal to rho VD. Oh, that's the Reynolds number. The hydraulic diameter is just going to be 4A over P, which we established previously would just be the 4 times 0.3 meters, 0.3 meters times 0.15 meters, times 0.15 meters, divided by the wetted perimeter P, which is 2 times 0.3 meters plus 0.15 meters. And I get a overall hydraulic diameter of 0.2 meters. So in other words, what we're saying with the hydraulic diameter is that this is roughly equivalent to a circular section of 0.2 meters. Not in terms of just cross-sectional area, but more in terms of ratios of cross-sections to perimeters, that kind of thing. It's roughly equivalent. This will behave, a pipe of this conduit will behave roughly equivalent to a 0.2 meter diameter circle. And then the Reynolds number if I consider the Reynolds number next, I'll have the same formula as before. The Reynolds number hydraulic would be rho V dH over mu. And this will be equal to 1.23 times, or just 1.23 kilograms per cubic meter, the density of air, times velocity, which was given as, let's see, we're given the velocity. No, but we were given the flow rate, so we can very easily calculate the velocity. And if you go and calculate the velocity, you will find that it is 1.511 meters per second times 0.2 meters. And then you can divide this by mu, which is 1.79 times 10 to the negative fifth, which will be Newton seconds per square meter. And I get a Reynolds number hydraulic is equal to 10,700, which is of course greater than our 4,000, so therefore this is going to be turbulent. This will of course then be turbulent flow, which means we have to use what to determine the friction factor?
Moody chart.
The Moody chart, yes, we're going to have to use the Moody chart or the Moody diagram. And again, I got the velocity by saying V is Q over A. That's not right. Equals Q over A equals 0.068. Just put a little note down here. 0.068 over 0.3 times 0.15. And that comes to 1.511 meters per second. So let's kind of scribble that down there, and that's how we would figure that it's turbulent. Next, let's figure out the friction factor. And the friction factor, I won't go through how to use the Moody chart again. That's fairly, we're going to use it the exact same way. Epsilon is going to be equal to 0.15 millimeters. 0.15 millimeters, looking at the chart and looking up the epsilon for a galvanized iron pipe. And then epsilon over the hydraulic diameter, epsilon over dH, is going to be 0.15 times 10 to the negative 3 meters. divided by 0.2 meters, our hydraulic diameter. And this will then come to 0.00075. And if we combine this with the Reynolds number, equal to 20,700, and we input both of these into our Moody chart, I get that the friction factor is equal to, or approximately equal to, 0.027. It's approximately equal to 0.027. And then finally, once I have the friction factor is 0.027, I can find the major loss fairly trivially. And this is what we're actually after, the actual amount of head loss over the course of the 12-meter pipe length. And this head loss is going to just simply be HL major is equal to 0.027 times 12 meters times 1.511 meters per second, quantity squared, divided by 2 times 9.81, acceleration due to gravity, meters per second squared, times 0.2 meters, and this then equals that the major head loss is simply equal to 0.188 meters. 0.188 meters. All right, questions on that?
One question.
Yes.
Is it supposed to be 20,000 or 10,000 for Reynolds number?
No, I calculate the Reynolds number is, I calculate it to be 20,000. Is that incorrect?
Oh, I thought you were 10,000 earlier.
Oh, did I do that?
You said it.
Oh, did I say 10,000? Sorry. Can you tell it's almost summer? Anyway, 20,700. Sorry about that. John.
General question.
Uh-huh.
I mean, you made the assumption that air was not compressible under that speed. Is that a pretty good, or is that
So the question is that a pretty good, that we assumed that air is incompressible at that speed? That's the question. And the question is that always valid, or when is that valid? And that's a good question. And I think in this particular problem, we were just given, that was a given that we were supposed to assume that air is incompressible. And that is something that is probably going to come down to a lot of experience, a lot of industry-specific experience. So if you're in an HVAC business, so an example would be like an HVAC business. So if we were designing, something like a HVAC system, that might be an example where air could be considered roughly incompressible. Because if you think about it, how would the air compress? Well, the air would compress, well, there might be some changes in temperature that would cause air to expand or contract, but once it's already at the same temperature and it's moving through the ductwork in a house or a building, well, the only way it's going to be compressed is if, well, the air in the pipes is essentially at atmospheric pressure, just slightly above or slightly below, right? And if you think of the very flimsy metal pipes that are holding up, that are holding this airflow, there's no way that it's going to be able to really those pipes aren't going to be able to contain very high pressurized air. They're just not. So it's going to be all about the same density no matter what. It's going to slightly vary here or there, but close enough for the calculation of head loss purposes. So, but it really depends on your application. So a lot of this would come down to sort of industry specific experience and knowledge. And in this case, we were just outright told, we didn't have to rely on years of experience. We could just say, well, I am telling you to assume that it's incompressible. It was one of our givens. But when you're actually working as a design engineer, then you'd have to use a certain amount of experience and really industry experience, industry knowledge to say whether this is truly incompressible or not. And when I say obviously nothing is ever truly incompressible, but you know what? If it's within a couple percent, your factor of safety is large enough on there anyway. If you're designing your HVAC system to fail at 0.1% error, well, you're not going to be in business that long anyway. So anyway, so let's move on and begin to talk about another topic, and that is minor losses. So we've mentioned major losses before, and we've heavily discussed those. And we have mentioned what minor losses are, but we haven't actually gone into some details on how to calculate them. So let us look at minor losses. And these again will appear in the in our energy equation. or a more final form of the energy equation. Really our final form of the energy equation, although we could also add pumps and things there if we wished. So let us consider minor losses. First of all, I'd like to compare and contrast major losses and minor losses. So minor losses are when you're at the store and you have a kid with you and you lose them in the mall or something. Never mind. That's a really bad joke. Oh my goodness. Okay. Get it? Minor losses. Ugh. Okay, so anyway, back to reality. Major losses can be defined as viscous dissipation, the viscous dissipation of energy, or viscous dissipation, as fluid travels through a long straight pipe. Through a long straight pipe. So in other words, these are frictional losses. Actually, I might rewrite this down here just to give myself a little more room. So in other words, these are primarily frictional losses. Meanwhile, minor losses are more localized. So major losses will always be measured with a friction factor that sort of represents the energy loss per unit length of pipe, or they'll always be measured in terms of energy loss per unit length of pipe. That concept really doesn't make sense for minor losses. They're more localized. So these are the kinds of things. These are losses from things like valves, bends, tees, entrance to pipe from tank, pipe or entrance to pipe from tank, or it could be the exit from pipe into tank. So an exit is going to be defined as an entrance. An entrance is going to be defined as going into a pipe. An exit would be out of a pipe. Exit to tank from pipe. From pipe. And basically, these are created from experimental analyses. We're going to have a, well, actually, I'll mention that briefly. So also from filters and from any other kind of local one-off thing. It's not something that occurs over a length of pipe. It's something that is confined to a single location. So instead of saying, okay, this pipe has so many losses of head per unit length, we'll just say this device, whatever it is, this bend, this valve, whatever, every time the water goes through it, it's going to lose X amount of energy. And that will depend on the velocity, but it's not a per unit length thing. It's just every time the water goes through there, it loses some energy. It pays a toll. Boom, that's it. And these are going to be based off of a coefficient, the loss coefficient. And so we need to find the losses. We're going to need the loss coefficient. And this would be KL in the book, I believe, or C in the FE manual. And so you'll have to look up a series of, these will always be presented in table form. I'm sure you can find similar tables like that in your textbook or in the FE equation manual. And essentially you'll find tables that list different types of restrictions for different coefficients for things like pipe restrictions or pipe components, expansions, contractions, exits and entrances, etc. So you'll go to your book or you go to your FE manual, and you will simply find the relevant table for the type of local appurtenance that you have, and you'll find the relevant loss coefficient. So these are determined experimentally. The geometry of these things can be quite complex. So while you can, analytically derive the, you can create a model and analytically derive, like, okay, if you have a circular pipe and you can treat it like an integral and you can integrate the energy losses across the pipe, you can predict some of these things. For the geometry of a valve or a bend or something like that, you obviously don't have fully developed flow there. You have kind of turbulent flow around those regions. So it becomes too involved to really try to solve for the losses there with an equation. So instead what you do is if I want to calculate if I want to figure out that if I make say I have a bunch of butterflies, so I'm interested in butterfly valves, which is a type of pipe valve. And what I do is if I want to determine that KL coefficient, and we'll see in a moment, the KL gives you the, or C, gives you the constant proportionality between H loss and velocity squared. And the way I would do, actually, let me just go ahead and write the final minor loss equation before I get into how you would experimentally determine these. So for now, you're gonna get you can just, for most of your purposes, you're just going to look up a loss coefficient in a table, but head loss minor is just going to be C times V squared divided by 2G. So C is your constant, again, constant from geometry. Measured experimentally. This is the kind of thing I would use, say, remember all those pi terms and the Buckingham pi terms and the similitude and dimensional analysis and experimental design, all that lovely stuff we talked about? This is the kind of problem you would use those for. So say you invented a new type of valve. So like you're a design engineer or you're a mechanical engineer, and you've got, you're dreaming one night, and in your dream you got a vision of this glorious new type of valve that's going to change the world and make you a bunch of money and make you a multimillionaire and all this kind of stuff, and you want to, you're going to sell these valves and make a boatload of money, right? Well, one thing that that if you're selling these for any kind of industrial use, it would be very nice if you could publish the C coefficient for various, you're probably not just going to make one size, you're going to make, one for 1 inch, 2 inch, 3 inch, 5 inch, whatever size pipe. And you would like to be able to, in your literature, show a table saying, okay, these are our loss coefficients for a variety of sizes. So you're sure, because you received it in a dream, and what's more trustworthy than dreams, that that this would be a great valve design, and you want to experimentally measure the actual loss coefficient C. So how do you do that? Well, you create some pi terms, you run through a bunch of tests, and you basically figure out, well, G is always going to be the same, and based off of, you basically use velocity as your independent variable, and it's going to be based on our experience with other minor losses, that's going to be proportional to velocity squared. So you just go and you run an experiment, you run different valve sizes through different kinds of velocity profiles. You measure the losses based off of, some pressure measurements to the left and to the right of the valve, and you can actually fairly easily directly measure these C coefficients. It's really not that difficult. You just have your, you have your valve here of some sort, and you have your pipe coming in and your pipe coming out. You measure the losses as the water has to flow around it or whatever fluid you're using. You measure the pressure here and the pressure here, and that the difference is going to be your pressure drop or your loss of head. And you try this at, you put in different velocities and you measure, okay, at 1 meter per second, we lose this amount of head. At 2 meters per second, we use this amount of head. And you can fairly easily just plot an equation for that, you fit that data to a parabola, and your C is just your coefficient. And that's it. This is actually, to describe that, it took a lot of words, but conceptually, this is actually fairly easy. how you would measure this. Now, actually measuring it, that could be one of the devil in the detail situations, but conceptually, measuring these things experimentally is not that difficult. So anyway, moving on, I would like to list an expanded energy equation with major and minor losses. So now let's look at an expanded energy equation with major and minor losses. So it would be the same kind of thing we've seen. Now we could also have a term for pipes in here, but I'll leave that out for, sorry, not for pipes. We could have a term for pipes in here. Now we could also have a term for pumps or for generators or turbines in here, but I'll leave that out for now. And so P over gamma plus V squared divided by 2G plus Z for point 1 is going to be equal to P over gamma plus V squared over 2G plus Z for point 2 plus our two loss terms. We're going to have two different loss terms. FLV squared divided by 2G plus 2GD, sorry, plus the summation of CV squared over 2G. CV squared over 2G.
That D or L?
Oh, that's a V.
No, I mean that one.
This one?
Bottom.
Bottom?
Next one?
This one?
No. D. It's a D? Okay.
Yeah, sorry, that's a D. If you can't read my terrible handwriting. And as a reminder, let me label these. So these are both fairly straightforward, our standard Bernoulli terms, but this is going to be our major losses, and this will be our minor losses. Question, why do we have the sigma here?
Because there could be multiple valves or...
Exactly, because there can be multiple local losses. Typically for this kind of equation, we're only running it for a single leg, the pipe. If I was looking at two different pipes, say I had a big pipe system with multiple pipe diameters, I would need multiple forms of this equation. I'd need multiple instances of this. But along a single pipe, I can have multiple valves, multiple bends, multiple T's, that kind of thing. So we need to consider both major losses and minor losses. All right, so let me work through a quick example here of one final example of calculating minor losses. And actually, in this case, I am going to calculate the K factor, the KL or the C. The book calls it KL, the FE manual calls it C. So consider an example. I have a furnace filter. I have a furnace filter. Let's see here. So I'm going to have some sort of furnace filter. Oh man, I need to change the filters on my my airflow thing, my air duct in my house. That's, yeah, it's good. Yeah, anyway. It's one of those things you always forget, but it's kind of important to do. So anyway. And I mentioned that I'm going to have point 1 here and point 2 on, so point 1 on the left side and point 1 on the right side. And then I have velocity 1 and velocity 2. And velocity 2. So again, this is a furnace filter. And I am told this is going to be at atmospheric pressure. P atmosphere is 14.7 psi. And this is air at 80 degrees Celsius. And I'm also told that V1 equals V2, or just is equal to V, equals 2.4 feet per second. But even if it wasn't given that the two velocities are the same, I would still find that a reasonable assumption, because this furnace filter is, well, it's not truly a pipe, but it's kind of in a pipe or in a duct. And so I feel that there has to be just as much air entering this side as leaving this side. Now, of course, we could get into the fact that it's compressible, but if we're assuming it's incompressible, then there has to be just as much going in here as coming out here, so it would make sense that the beginning and end velocities are the same.
That's also
That would be 80 degrees Celsius. And then delta P over, we're also told that delta P over gamma is equal to 0.06 inches water in pressure. Sensitive inches mercury, inches water. And from that we can conclude that delta P over gamma water equals 0.06 inches. Okay. And we're given all of this, so all of this is given, and I want to find KL. Or C if you prefer the FE manu form. All right, so let's work to the solution quickly here. So we're going to start with the Bernoulli, or the energy equation. And the energy equation, let's look at this. P over gamma air plus V squared over 2G plus Z for position 1 is going to be equal to P over gamma air plus V squared divided by 2G plus Z for position 2 plus our losses, which will be KL V squared over 2G. And we'll have only minor losses, we'll not have major losses. Then I know that Z1 equals Z2 because we're not stated that there's any kind of elevation change. Plus, even if this thing were at an angle, it's so small, the change in height would be minimal. So Z1 equals Z2, and V1 equals V2. So that means that this term and this term cancel out, and this term and this term cancel out. And that I can turn the P1 and P2 into a delta P, which is what I'm given. So I was given the pressure drop. In other words, just the drop in pressure along the way. So delta P divided by gamma air is equal to KL V squared divided by 2G, which leads us to that that delta P is equal to KL V squared rho air over 2. Basically, if I divide, well, I guess I would be, if I'm just thinking about this, I would be dividing gamma by G, I guess, to get the density. So rho air over 2. Okay, so I have that, and I want to find delta P. And this is going to be, so I start with the P absolute divided by RT. Divided by RT. Actually, not quite, sorry. Let's find delta P. We're told that it's delta P divided by gamma W. Or we're told that delta P over gamma W is equal to 0.06 inches. And from this, we can get that delta P is equal to 0.06 inches times 1 foot per 12 inches times the density of water, which is 62.4 pounds per cubic foot. So this means that our delta P, our drop in pressure, is going to be 0.312 pounds per square foot. Pounds per square foot. So the real devil of this problem is going to be our unit conversions. 0.312 pounds per square foot. And then I want to solve for KL in energy equation. Well, I could say I need the actual density of air. So rho air is equal to P absolute divided by RT. R times T, our gas constant times the temperature, equals, this is the ideal gas law. 14.7 psi times 144 inches squared per foot squared. Then divided by a R of 1716, and this is a lovely unit here, pound foot per slug Rankine. And if you remember from chemistry class or from other applications of the Eddy gas law, you cannot use a scale like Fahrenheit or Celsius. You have to use a absolute scale like Kelvin. Although we're doing English units, I'm going to use Rankine. And if you don't remember or don't recall or are not familiar with the Rankine scale is to Fahrenheit like the Kelvin scale is to Celsius. So yes, we're digging out R, which is degrees Rankine. Lovely. And then times 459 plus 80 degrees R. So to the conversion factor here, or not conversion factor, conversion sum, I should say. If you have something in Fahrenheit, you just add 459 to it, and you get its absolute temperature in degrees Rankine. I love this problem. I love problems with just really esoteric units. It's great. We got, oh my God, this is so beautiful. We have slugs, we have Rankine. I mean, what more could you ask for on a Monday morning or a Wednesday morning? What more could you ask for? Oh yeah, we could put some furlongs in there, maybe some fortnights. Anyway, or how about the unit of a barn? That is a unit. It's a measure of atomic cross section. It's like 10 to the negative 20 something square meters or something like that. Yes, or the Larson, yes, the Larson. 0.00228 slugs per cubic foot. Slugs per cubic foot. And then the KL is going to be 0.312 pounds per square foot. So I got my density here in slugs per cubic foot. Pounds per cubic foot times 1/2 times 0.00 times 0.00228 slugs per cubic foot times 2.4 feet per second quantity squared. 2.4 feet per second quantity squared, and KL finally will come to 47.5. And now once I have it for 1 point, I could measure the K. Once I know that, I can predict the head. I can predict the head loss for any velocity change. So actually, in this case, we don't even have to plot a velocity curve or a curve versus velocity. We can just go and calculate it directly. All right, that'll do it for today. If you have any questions, feel free to email me or see me during office hours. And as always, thank you.